plane. What important over here is we still need to find out two things. One is magnitude. The other one is, of course, phase. So the magnitude in body diagram, we're talking about dB. But when we are using another plot, we just talk about the ratio. But it doesn't matter what you do. The magnitude is always defined as output over input. Okay, so it doesn't matter what you represent the magnitude. It's always the ratio between output and input. If you use body plot, the unit over here is dB. If you are using a quiz, it's just the ratio, original ratio. Do we have any unit since it's a ratio? No. So it's just the if you have output equals to several volts, it means that your input is several volts. So something like that. And the phase is, again, delay between output and input. So this one over here, we always use degree. Okay, so those are two things which are always important, and it's different from S domain or S plane. When we are talking about S plane in locus, what are we drawing? We are drawing the position, locations, poles, trajectories, movement, poles, and zeros, right? So if our K is increasing, then the pole location of the overall system is going to change its position. So that is, we have put S plane. And when we say we have S plane, the important thing is that we do not have pole location goes to the right hand side, right? That's the only the only thing. But over here we are talking about L plane. Still, we are talking about real S's and imaginary S's. But this time we are not talking about the pole location. We are talking about the ratio between the input and output. So if you are putting the magnitude, output over input, if we do not take the absolute value, originally we should have real part and imaginary part. When we try to find the magnitude, we are taking the square root of the imaginary part plus the real part together, then take the square root of the combination of those two. That is our magnitude, right? You guys still remember what I'm talking about? But in an L plane, we are not going to separate. We are not going to combine them together. Instead, we're going to plot the real part and imaginary part separate on the imaginary S's and the real S's. So that's the difference between this one and this one. You might be confused because those two are talking about real S's and imaginary S's. But when we are talking about those two planes, they are actually different ones. So in this part, in particular, for the Nyquist part, for the Nyquist plot, we are trying to represent body plot into the L plane. So we are not using two plots anymore because when we are using body, we need to separate the magnitude and the phase into two different plots. But when we are talking about Nyquist, they are actually together. So that's the reason when we are talking about this part, we are using this one. And hopefully, we are not going to encircle this specific position, because if we encircle this specific position, it means that our system is, if we just touch this position, it means that our system is critically stable. If we enclose this one, it means that our system is going to, the pole location is going to located at the right hand side. So this point over here is something we are not going to enclose in, when we are doing Nyquist plot. So to be specific, how are we going to draw our Nyquist plot? Let's use one of the example to do the plot. We haven't talked about this one, right? So we would like to plot the response, which is this. So obviously, this one is unstable, right? But when we put the closed loop of this guy, can we stable the unstable system into a stable one? We can, right? Because when we put everything all together, let's say we have a K, what are we going to have? We are going to have s minus 1, s plus 1, 2, k, 1 plus k, s plus 2, s minus 1. The closed loop is going to be like this, right? So if we separate, if we combine both sides together, is it possible to stabilize everything? It's possible, right? As long as we are not going to have the closed loop pole equals to goes to the right hand side, this system is going to be stable, right? So by looking at this part over here, we can say the maxima k is going to be what? 2. Does it make sense? Because now I have a constant over here which is 2, and k multiplied by minus 1. If we have k equals to 2, everything becomes the constant term becomes 0. But if k is greater than 2, our system becomes unstable. So by looking at this, we know that. So how are we going to verify everything using Nyquist plot? This one over here is just an example because it doesn't really require us to use Nyquist plot or Lewis-Hurwitz method to do the analysis. We can visualize this one quickly. But if we want to do frequency analysis for this one, and we are not interested in using body plot, how are we going to do that? We are going to use what? So what are we going to do is, first, we replace S with J omega, then L J omega is going to J omega minus 1, J omega plus 2. This is nothing new to everybody, right? Because when we are trying to do body plot, we are using the same analysis. The only difference is that when we are doing body plot, what are we doing? We are taking the absolute value of this one by replacing the omega with different frequency number. We can know the absolute value of this part, then we can find out what is the magnitude between output and input, and that is how we do the analysis. The other thing is we use this one over here, take the real part and the imaginary part, and use arctangent. Then we get the phase. So everything remains the same. But the difference over here is we are not going to take the absolute value for the analysis over here. So when we are trying to do something like this, we do or we don't, it doesn't matter. what we're trying to do is we have j omega plus 2, j omega minus 1, j omega minus 2, j omega minus 2. So this part over here is what? 1. When we are doing that, it is going to be and over here it becomes right? So so this is going to be my real part and my imaginary part. Something like that. So there are two ways you can do the analysis over here. The first one is if you still want to do the absolute part, or you want to do this part, it doesn't matter. So let me show you this method first. So when we are trying to do something like this, it is going to be okay, nothing fancy. I'm just taking the absolute value of this part and this part and getting the constant out of the analysis, then I get this absolute value. So this is everything similar to what we have in body plot. The only difference is I'm not getting the dB value of this one, I just take the ratio. Second thing is I still need to find out. So we can do from the basic, it is going to be tangent negative omega, because this is in the numerator, so it is going to be a positive value, and this is denominator, so we need to have a negative sign. Hold on, I think I make something wrong. Hold on, I think before I do that, I should do something. Sorry, I made a mistake earlier. So when I do the analysis, this is a typical way we can do the analysis, taking the real part and the imaginary part out of the equation from the beginning. But if we follow the method, we deal with body plot. This is magnitude. Those two are actually the same thing. So if we take the magnitude, it is going to be 1/2. Right? Nothing different, but we have this one and we have this one. And for the angle, we got the negative sign in front of it. So when we have negative sign in front of it, what do we have? We have negative 180 degree directly because it's a negative sign. Now we take care of the real part, the numerator part. Since this is a numerator, this is going to be plus tangent imaginary part divided by real part. So it is going to be negative omega over 1. This is in the denominator, so we should have what? Negative sign in front of it. And my real part, my imaginary part is going to be omega over 2. My real part is 1. So I got my a magnitude part and my phase part all together. That is going to be my first method. For the second method, since we get this part out, so I can take my real part of the whole thing plus J, the imaginary part of the whole thing. Right? So you can take, because we're going to put the number into this one, so every time we put the number into this one, we get the real part and we get the imaginary part all together. And my magnitude is going to be the coordinate of x position and y position based on this configuration. And the phase is going to be arctangent. Do we care about this part? We don't, because if we have something like this, it is going to be this is going to be just a constant, and the constant or the gain doesn't really affect the phase of everything. So this part we don't need to worry about, but we do have a negative sign in front of it. So we have negative 180 degree. And the other part is we are going to have omega divided by minus omega squared. So it's just imaginary part divided by the real part. And that is from the equation we have over here. So either you want to use that one or you want to use this one. That's one. Okay? Everybody realize we're talking about something. The magnitude can be represented into two methods. One is the absolute value. The other one is the real part plus the imaginary part. But how are we going to use those two altogether? I'm going to draw that in the middle. So as I said earlier, we are going to plot everything on L plane. So I'm replacing S with L on this plot. Okay, so I'm going to plot the magnitude and phase on this one instead of the position of pole locations on this one. Does that make sense? So when I'm doing that, there are a few things we want to do. Let's generate omega L phase L. So let's say I have 0. I have 1, I have 2, I have 10, I have infinity. So if I use this method over here, when omega equals to 0, what is my magnitude?
1.
1.5, right? What is my angle?
Minus.
This is 0, this is 0, so both of them are 0. So it's going to be minus 180 degrees. If you put everything over here, this part is going to be 0, and this part is going to be 2/4. So it's going to be negative 0.5, right? It doesn't matter what you do, it's going to be something like that. So if you put negative 1.5, it means that the magnitude is going to be 0.5 and the angle is going to be minus 180. So with that said, let's say this point. Let me explain everything larger. So if you use this method, it is going to be 1/2. So you have a circle, 1/2. But the angle is going to be negative 180. So do I put my plot over here or over here? Right hand side or left hand side? Negative 180 degree.
Left hand side.
So this one is not clear. Let me use yellow. So this point over here is omega equals to 0, and this is going to be 1/2. If we put omega equals to 1 over here, what do I have? I have 1/2 square root of 2, 1 plus 1 over 4. So this is about 0.7 magnitude-wise. But when we consider magnitude, what are the things we need to consider as well? Phase. So if we do we get about negative 251 degrees. So what are we going to do? 0.7 is about this large. That's a magnitude. And we put a radius. It's about, the radius is about 0.7. Now, I say the angle is negative 251 degrees. Where am I looking at? This is minus 180. But let me do the imagination. It should be this point or this point. The second quadrant. Everybody know what is quadrant? 象限. So it should be the second one or in the third one. Second one, third one. Keep in mind, what kind of angle are we having? Negative 250. So when you say negative 250, are we start from here or from here? From here. So this is negative 180. Negative 250 something is over here. So I think it's about 70度、71度左右。So it's about over here. Okay. Then if you do 2, the omega equals to 2, you're going to find this one over here is close to 0.8. And the angle becomes, now let me ask you a question. What are we going to do? The magnitude is just a little bit more. So it's about over here. And we got negative 288 degrees. Which quadrant will I draw the position? First quadrant, second quadrant? First. Second. I have no idea what the hell you're talking about. 用中文。这 这两个部分没有问题吧？这叫什么 magnitude 大小比就速的比值，然后这是 phase 就相位差 delay。那我们一开始说它负180度，从这边开始算，这样是正的；这样开始算，这样是负的。那我们第二个是负251度，就要从这里0度开始，往这边推251度，所以它会落在第二象限。这个的话，它是负288度，那它从这里开始往回推，超3个象限是多少度？270，所以它应该会落在大概这附近，18度左右的范围。所以你这样做就好。Okay, so why do I need to say that? So you can see as my omega changes value, the dot I'm moving from omega equals to 0 to omega equals to 2. So if you replace omega with 0.1, 0.2, 0.3, gradually you're going to find individual points along a trajectory. Now, I actually didn't calculate this one, but I do calculate this one. If we put our omega equals to infinite, what do we have over here? This is the infinite. So 1 is going to be ignored. The only thing that over here is going to be 1/2 in the bottom because this is a square root. So this is 1/2. 1/2 multiplied by 1/2 becomes what? 1. How about the phase? This is negative 180 degrees. Since this is positive, and this is going to be another one, so you're going to find the angle is actually negative 360 degrees. So when I say it's going to be magnitude equals to 1 and the angle is negative 360 degrees, where am I going to draw my